thanks for that. Yeah, can you guys hear me now? Awesome. Okay. All right, it's 5:30. Let's go ahead and get started. Although actually, okay, good. Nathan's here. Okay. All right. So good afternoon or good evening, everyone. How's everyone doing today? Good. Tired? I know, I'm tired too. All right, and so before we begin today, we actually have an announcement. And so I'm gonna go ahead and turn the floor over to Nathan, and then we'll start maybe about 5 minutes. So go ahead, Nathan. Thanks.
Hi, everybody. I hope everyone's doing well. We're getting into night class right now, right? So my name is Nathan. I work for ECS, Graduate International Admissions Office. So I handle a lot of the applications that comes into grad school. So if you're thinking about grad school, I'm the person to talk to. Has anyone thought of grad school by any chance? Yes, no? No, they're like, no, okay. But if you do have an interest, we have a grad info session event that's happening on November 9th from 12 to 1 p.m. We are gonna have pizza there, food, snacks, drinks, and then first 20 minutes, we'll talk about the program requirements, as well as the admission requirements, the process, how fast the turnaround is for your application since you graduated here from Cal State Fullerton. And then that's about it. So, and then the last 30 minutes, we're going to be going into breakout sessions if you wanted to talk to your graduate department in terms of like the logistics on the classes you'll be taking. So, and I've heard with some of the programs, I think it's like an extra, let's say 9 or 10 classes, and then you'll be able to get your master's degree. So if you are interested, anyone in the chat here, I'll click open the chat just in case anyone has any questions. Okay, no questions yet, but yeah, so if you're interested and you're on over Zoom, I'll go ahead and send Dr. Trin the flyer, which has the QR code to sign in and RSVP, get a free slice of pizza and all that around. So other than that, if you do want to have a one-on-one with me, I'm located in room CS311. And yeah, so hopefully you all have a good rest of your semester. And if you have any questions, let me know. All right. Thank you very much.
Awesome. Thanks, Nathan.
Thank you, Dr.
Yep.
Appreciate it. I want to scan the QR code even for a slice of pizza or anything. Oh, you did? Oh, you did? Nice. Okay, well, good to see you again. So, all right, take care.
Yeah, I see Nathan.
Take care.
Yeah, graduate school is a great option, and so Nathan's going around. He's talking to a lot of junior level courses, just because I think it's an option that not a lot of people know about. And so, kind of in a world where you kind of have to really do a lot to kind of stand out on your job applications. Grad school is a great way to do that. And so, the program that Nathan is talking about is, I think you'll hear a lot about it from other schools in terms of like a 4+1 program. And so the idea is that, you've already done undergraduate here. You probably already satisfied a lot of the requirements. You're already in the system. And so to get a master's degree is probably going to take you an extra year to do it, or maybe a year and a half. And so in terms of like investment, it's a great investment of your time because it really opens up a lot of job opportunities for you. The starting pay is usually a lot higher for a master's degree student too. So, it's a good option. And so if you're interested in learning more, definitely, hit Nathan up. I'll give everyone his contact information too. So you can send him emails, or if you want to talk to me too. My grad school experience was a bit different because I was in grad school for 6 years, but I have a lot of friends that did kind of this extra, an extra year of coursework, or maybe extra year and a half, and they're in great spots in their career right now. So I'd be happy to talk to you about that. I think one question I get asked a lot is that if it's competitive, generally speaking, not as many people go to graduate school for engineering as undergrads. So it's a lot easier to get in. And so it's kind of more a decision if you want to do that. Do you want to dedicate another year or so of your life to going to school versus going out there and working? And so that's kind of the primary question in terms of whether or not I'm going to get in or not. So yeah, and so if you want to talk about it, I'm open to talk about that. But I think it's a good option for a lot of people. Okay, all right, and so that was kind of a quick break from our usual scheduled programming, and so in terms of finite elements, I know probably what's on a lot of people's minds right now is the project, and so I've answered a lot of questions about that the last few days. So remember, the project is due this Sunday, and so the project is due October 30th at 11:59, and so make sure you're aware of that. And if you have questions on setting up the simulations, whether your boundary conditions make sense, whether your mesh looks good, I'm definitely open to talking about that all throughout this week. And so, definitely come by to office hours, show me what you have. If you have questions, send me an email. I'm more than happy to help. Okay, so definitely make use of that. Okay? And then after this week, I'll assign the next homework assignment, which is going to be on this stuff, the direct stiffness stuff. And so, I know we've gone, maybe over 2 weeks now of this stuff, but we haven't really practiced it, but that's going to be your chance to practice it. All right, questions. Will there be dedicated time on Thursday for the project? There won't be. So I plan on lecturing, today and Thursday. And so project is kind of just on your own time. Okay. All right. And so, I didn't write the learning objectives today just because we're kind of picking up right where we left off. And so, I'm just going to do this example. But are there any questions about the project or anything in general, before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. And so, where we left off last time was a question. Can we edit the geometry? Yeah. If you, I don't mind if you edit the geometry. And so if you, that could actually be one of your separate conditions too, or one of your separate simulation situations. And so I just, I've been talking to people today and people were asking me if you can change the material properties as a different condition. That's definitely possible. But if you want to change the geometry for a different condition, you can definitely do that as well. So yeah, definitely. I think some geometries will be easier to do that with. I think the bracket will probably be the easiest one because I think that one's an actual design modular part. And so I think you can actually open that up and change that. But yeah, feel free to change the geometry. Yep. Okay, and so where we left off last Thursday is we were talking about how to do two-dimensional direct stiffness problems. Okay, and so we kind of spent a good amount of time. Let me kind of scroll up a little bit, driving this this monstrosity right here. And so remember this right here. This is the element stiffness matrix for a 2D truss element. Okay. And the reason we kind of spent so long deriving this is that when we do 2D problems, we want to make sure that we compute element stiffness matrices in the same coordinate system for every element. Okay. Because what can happen, let's say in an example like this, let's say we have 3 elements. Each of these 3 elements are oriented in a different direction. And so, when we're going through our finite element process here of, element stiffness matrix, assembly, for some reason I can't scroll up. Element stiffness matrix, assembly, boundary conditions, and solving, we want to make sure that all our element stiffness matrices are in the same coordinate system. There we go. Because if they're not, if they're all derived within their own local coordinate system, we can't actually assemble them into the same, global system because they're all going to be relative to different parts. Okay, and so that's why we have this kind of complex 2D element stiffness matrix that contains a lot of sine and cosine terms. Okay. Okay, but besides that, the process that we're going to go through is exactly the same. So we're going to go through this 5-step process of labeling the geometry, discretizing it, computing the element stiffness matrices, assembling everything, applying boundary conditions, and solving. Okay, so it's the same 5-step process. It's just that it's going to take a lot longer because the element stiffness matrices are a lot bigger than they were before. Okay, and so we kind of left off doing this example here. And so what we have is a 3-element system, and so we have 2 truss elements and 1 spring. Okay. And what we're interested in computing is the nodal displacements of the 4 marked nodes. And so node 1, node 2, node 3, node 4. We want to compute those displacements based on the orientation of the truss elements and the load that's being applied. Okay. All right. So of course, we have the properties, the material properties for the elements. And so for the truss elements, we have a Young's modulus, we have the cross-sectional area, as well as their length. And then for the spring element, we have its spring constant, which is 250,000 pound per inch. Okay. Okay. And so to analyze this structure here, we're going to go through our direct stiffness methodology. And so our first step is going to be to derive the element stiffness matrices for each of the elements. Okay. And so we're going to start with element A. Okay. And element A is our vertical element here. Okay. And so what we said for element A is that, the first thing we have to do is to compute its orientation. Okay. And so relative to the positive x-axis, element A is rotated up 90 degrees. Okay. And so what we say is basically the theta value for this is 90 degrees. Okay. And so the next thing that we're going to compute here are the sine and cosine of that angle. And so at 90 degrees, it's actually really simple because the cosine of 90 degrees is 0. The sine of 90 degrees is 1. Okay. And when you have one of these sine or cosine terms equal to 0, what that's going to do is that it's going to cancel out a ton of the terms in the element stiffness matrix. Okay. And so when we plug in cosine of 0, cosine is equal to 0 and sine is equal to 1, and we plug that into our element stiffness matrix formulation here, we get the following element stiffness matrix. And so we said that Ka is equal to 5 times 10 to the 5th multiplied by this matrix where the majority of it are zeros, and we just have ones on some of the locations. Okay. Okay. And of course, oh, and one thing before I forget too. And so remember, whenever you compute the element stiffness matrices, you have to indicate which nodes the element is acting on. And so for node A, our element A, it's acting on nodes 1 and 2. And so we can denote that here on the vector on the right. So we have d1x, d1y. That's the x and y deformations for node 1. And then we have d2x, d2y. That's the nodal deformations for node 2. Okay. All right, and so that's just a recap of kind of where we were at the end of last Thursday. And so we're going to go ahead and continue this example, and then we're going to see how we go from there. Okay. Any questions on this? Okay. All right, so let's go ahead and continue. Let's look at element B. Okay, so element B here is a spring, right? Our question, so d1x and d1y is used for all the elements? Yes, yes it is. Yeah, because all the elements are attached to node 1 right here. They're all going to involve d1x and d1. Yeah. Okay, and so if we go back up to the figure here, we can see that element B is the spring, and it's kind of rotated up towards the top right. And so the angle that element B makes with the positive x-axis okay, so the angle that it makes is 45 degrees. Okay. So that's going to be theta. And so I wrote that out because for this example, it's the angles are kind of exactly as they appear in the figure. But in the next example, this kind of definition of the angle as the angle that it makes with the positive x-axis, that's going to be kind of key to the next example. And so that's why I kind of wrote it out there. Sinuses. Okay. And so with a theta value of 45 degrees, let's go ahead and compute sine and cosine. Okay. And so we have C. C is cosine of 45 degrees. And so cosine of 45 degrees is √2/2. And sine of 45 degrees is also √2/2. Okay. Okay. And so KB Technically, we don't have the element stiffness. We haven't computed the element stiffness matrix for a 2D spring, but we can kind of easily derive it. And so, if you look at the element stiffness matrix for a 2D truss, you can see what's out in front is this AE over L. Okay. If this were a spring, all we're going to do is we're going to replace this with the spring constant K. Okay. Everything else on the inside is going to stay the same. So all the sine and cosine terms are going to be the same because we kind of derive those without really any knowledge of the truss anyway. And so for element B here, our element stiffness matrix is going to be the spring constant K multiplied by all those terms there. And so just for completeness, let me go ahead and write it down again. Okay. And so we're going to have cosine squared, cosine sine, minus cosine squared, minus cosine sine, sine squared, minus cosine sine, minus sine squared, cosine squared, cosine sine, and sine squared. Okay. Okay. And of course, this element stiffness matrix is symmetrical. So, the bottom half is going to be just the same as the top half, just reflected over. Okay. Okay, so let's go ahead and plug in for this. And so for this element here, we have our spring constant is 2.5 times 10 to the fifth. And then we're going to start plugging in for the cosine and sine terms. So first we have cosine squared. Root 2 over 2 squared is just 2 over 4. So that's going to be 1/2. Cosine sine is going to be root 2 over 2 times root 2 over 2, which is 1/2. Minus cosine squared is minus 1/2. Minus cosine sine is minus 1/2. Right. I would say, among all the different angles that the elements can have, 0 degrees, 90 degrees, 180 degrees, 270, those are the most ideal because those are zeros. But second place to that is 45, because 45 degrees, you end up with just a bunch of 1/2s. Okay? The only thing you have to worry about is just the sines. Okay. All right, and so remember the trick that I taught you last time is that, whenever you have a symmetric matrix, what you can do is that you can kind of build it up, start with the first row, and then as soon as you're done with the first row, write that into the first column as well. Okay, so I kind of do this row, column, row, column, row, column. Okay. Okay. So for the next row, we have 1/2 minus 1/2 minus 1/2. And I'm going to write this into the column as well. And then I'm just going to continue from there. And so we have 1/2, 1/2, 1/2, and 1/2. Okay. So that's the element stiffness matrix for element B. But then, of course, we're not done yet because we need to specify which nodes that this is acting on. Okay. And so element B here is acting on node 1 and node 3. And so, we're going to specify it that way. Okay. All right, and then finally, we're going to look at element C. And so element C here, the theta value is 0 because it's perfectly horizontal. Okay, so we go back up to the figure here. Okay. And so element C here, that's the one on the bottom. And so because it's perfectly horizontal, that theta is going to be 0. Okay. And so with theta E is equal to 0, we have cosine. Cosine is going to be equal to 1, and sine is equal to 0. And just like before, when we have a 0 for the sine or cosine, that simplifies things a lot because a lot of things are going to cancel. And so basically any term that you see that has sine We're just going to set that equal to 0. Okay. Okay. And so for the element stiffness matrix for element C, we have 5 times 10 to the 5th. Remember, this value here is obtained by taking A times E divided by L. And I'm just going to go fairly quickly here, just because with a sign is equal to 0, then most of the element stiffness matrix here is going to be 0. Okay, so we end up with an element stiffness matrix like that. And then since element C here is connected to nodes 1 and 4, then we're going to indicate that like that. Okay. All right, and so that's step 1. These are our 3 element stiffness matrices. Remember, you should get 1 stiffness matrix for every element. Are there any questions on anything we've done so far? Okay. Okay. So now that we have the element stiffness matrices for each of the elements, the next step is to assemble. So this is the step that gets a little bit difficult to do. Okay. All right. And so we have 4 nodes in this. We have 4 nodes in this problem here, and each of the nodes has 2 degrees of freedom associated with it. And so because we're in 2D, we have to consider both the X and Y components of their displacement. And so our global linear system, or our global stiffness system, has to account for that. And so, for 4 nodes and 2 degrees of freedom per node, that means that our global linear system here is going to be 8 by 8. Okay. Okay. So that means 8 equations and 8 unknowns. So, all right. So I want to make sure I give myself a lot of space for this. Okay, so first let's write the forcing vector. And so we have F1x, F1y, F2x, F2y, F3x, F3y, F4x, F4y. Okay, and then we have the corresponding row. So D1x, D1y, D2x, D2y, D3x, D3y, D4x, D4y. Okay. And I'm going to go ahead and label the columns as well, because we're going to need to stick in the element stiffness matrices into each entry here. Okay, so we have D1x, D1y, D2x, D2y, D3x, D3y, D4x, D4y. And so it's as we start to do more and more of these problems, more and more complicated problems, it starts to get more and more difficult to squeeze it into one page. And so what I see a lot of from students is that once we kind of get to this section here, a lot of people actually do their homeworks kind of horizontally instead of vertically, just because these matrices are so big, and so they need more space to kind of write it all down, which is fine with me. Okay. And so we need to insert our 3 element stiffness matrices into this global system. And remember, the locations of where we insert it depend on the degrees of freedom that they act on, okay? Or the nodes that they act on. Okay, so let's start with element A. So element A is the simplest. And so element A is going to act on nodes 1 and 2. Okay. And so that includes both the X and Y deformations for that node. Okay. So we kind of box it out like this. So the nice thing about element A is that it's all going to be one contiguous piece. Okay. And so we don't have to split up any of the quadrants here. And so that's going to be where element A is. Okay. And let me do this just to make things easier. So I don't have to write 10 to the 5th every single time. What I'm going to do is I'm going to factor out that 10 to the 5th. And so the 10 to the 5th will kind of live outside here. Okay. And so on the interior, we're just going to have just whatever the coefficient in front of that is. Okay. And so for element A, we have, 0, 0, 0, 0, 0, 5, 0, minus 5, 0, 0, 0, 0, 0, minus 5, 0, 5. Okay. Okay. So that's element A. Okay, element B is going to be nodes 1 and 3. Okay, and so this is a little bit tricky because we have to kind of split this up. So remember the way that we did this in the 1D case was that we kind of had 4 different quadrants at different sections of the stiffness matrix, and so we're going to have that here as well. Except instead of just kind of one off square, we're going to have 4 different quadrants of 2 by 2s. Okay, and so let me kind of show you what I usually do. And so remember, the element stiffness matrix is going to exist at the intersections between these 2 nodes. Okay, and so for instance, let's go to the node 1 column or node 1 columns, which is these first 2 right here. Okay, and the node 1 rows, which are these 2. And so kind of the intersection for those 2 is going to be right here. Okay. And so that's kind of the node 1 block that contains both the X and Y deformations for node 1. Okay. Next, we have the intersection between the node 1 row and node 3 columns. And so that's going to be these right here. Okay. And so that's the one of the node 1, node 3 blocks. Okay. The other one is going to be for the rows for node 3. And so we go to the D3X, D3Y rows. But then we still stay in the D1X, D1Y rows. Okay. And then finally, we're going to go to the node 3 section, which is right here. So it's the intersection of D3X, D3Y column, and the D3X and D3Y row. Okay. And so let's go ahead and add in the values. And so remember, whenever you have element stiffness matrices that overlap, all we're going to do is just add their values together. And so up here, we're going to have unfortunately, it's a bit awkward, but we have 1/2 multiplied by 2.5 times 10 to the 5th. Okay. Remember, we have 10.5 or 10 to raise to the 5th power on the outside. And so we're going to have a plus 1.25, plus 1.25, plus 1.25, plus 1.25. Okay. And then here we have a minus 1.25, minus 1.25, so on. Okay. Okay. And so that's what we have for that one. Finally, we have element C. So element C here is, it acts on nodes 1 and 4. And so I'm going to just go ahead and repeat the same things. Okay. First thing, we have node 1, which is up here in the top left. So kind of a lot of action in that section right there. Then we have that section there. Section there. And then that section right there. Okay. All right, and so once again, we're just going to add together the values. And so thankfully, most of these are 0. We're going to have a plus 5 in the top left. Everything else there is 0. And we have a minus 5, 0, 0, 0, minus 5, 0, 0, 0, and then 5, 0, 0, 0. All right, and so these, the assembly for these ones can be a bit, a little bit tedious, I would say, just because you kind of have to keep track of, which 2x2 section goes to which section, okay? And it's very easy to kind of get lost here. And so, definitely the most important thing here is to kind of just stay organized. Use a boxing strategy like this. And so if you're working on a situation where you have different colors, that helps a ton. If not, maybe use different line styles for marking off the different sections of the matrix. And so, this is, definitely a difficult step. And so you want to make sure that you do it carefully, because, if you shift, what I see a lot is that, people kind of shift the boxes up one, or maybe to the right one, just because it's hard to read the columns, especially for matrices that get to be like 10 by 10 or 12 by 12. And so you really want to kind of be careful with these ones. Okay. And of course, everything that's not marked here, we're going to go ahead and fill it in with zeros. Okay. And that right there is our assembly step. All right, any questions on the assembly? It's a lot. Yes, I know. Yeah, it's definitely not a comfortable, not okay. I'd say it's comfortable, but it's not fun. There's definitely a lot better ways to spend 20 minutes of your time than writing out these giant matrix systems. But I also kind of want to highlight during these sections of finite elements. Almost no one does it by hand. The only people that actually do finite elements by hand are just people that take a class in it, because you have to understand the theory. And so finite elements was really kind of designed to be a computer algorithm, because for a computer, this is no problem. And so what a computer is really good at. Yeah, typing out might be easier. What a computer is really good at is that if you can give it a very structured problem that may require a lot of busy work, but is fairly structured, a computer is awesome at doing that. And so, and this kind of fits the bill perfectly. And so, a problem like this where you have to construct a really big ass matrix with a lot of element stiffness matrices, a lot of rows, and a lot of columns, where if you were to do it by hand, it's extremely tedious. Where for a computer's like, this is no problem. I can do this, in no time. So, you can see that even for, I would say this problem here is still within the realm of very, very simple finite element problem. And so, even then you can start to see that it's starting to get a little bit ridiculous. And so, it's these problems can really get away from you really quickly. Okay, and so that's the assembly step. And so of course, we're not quite ready to solve yet. And so the next step here is going to be to apply boundary conditions. And so remember, for our boundary conditions, we have our fixed supports as well as our loads, okay? So let's start with the fixed supports. And so in particular for this problem, we have a lot of them. And so for this particular problem, we have fixed supports on nodes 2, 3, and 4. So if you look back at the problem geometry, you can see here that node 2, node 3, and node 4, all three of these are attached to pin supports. Okay, and so what that means that those displacements are going to be 0. Okay. And so that goes for the X and Y displacements. And so anything that has a 2, a 3, or 4, we're just going to apply our fixed support to those ones. Okay, so let's go back to the system here. Okay, so node 2 is of course going to be these two rows. Go ahead and circle that. Okay, that's node 2, or everything associated with node 2. These are the rows associated with node 3. These are the rows associated with node 4. Okay, and so we're about to basically annihilate all these rows in the name of the fixed support. Okay. Okay. And so remember, what we do for fixed support is that we set the forcing vector equal to 0 for those ones. Okay. So F2x, F2y, F3x, F3y, and F4x and F4y are all going to be 0. Okay. And then the other thing that we do is that we eliminate the row, each of the rows associated with those fixed supports. Okay, so let me do it for node 2 first. Okay. And then what we're going to do is we're going to replace that with a row of mostly zeros, except for a 1 on the diagonal. Okay. So for row 3, which is associated with D2x, we're going to put a 1 on the third column. And for D2y, we're going to put a 1 on the fourth column. Okay. I'm going to repeat that same process for the other two, for the other fixed supports as well. Okay. I don't know why my iPad is omega lagging right now. Okay. Okay. And then finally for the last row as well. 2 rows. So I know what you're probably thinking right now. And so you're probably feeling a little bit upset. And so you might be wondering, why do we go through all that work to assemble this linear system if we're just going to eliminate all those 6 rows to begin with? And you would be right. And so, I agree with you. And so, as you kind of start to get good at these, and so as you kind of do more and more, you can definitely take shortcuts like this. And so you can say that, I know that this node here is going to be completely fixed. And so I'm not even going to bother assembling the matrix for those elements. Okay? The key here is that you kind of have to know what you're doing. And so what tends to happen, and I see that every single semester, is that, I know these problems are very time consuming. They take a lot of time. And so the temptation is to kind of take some shortcuts like this, is to, I know these nodes are fixed, and so I'm just going to go ahead and fix it. But if you are not kind of well practiced in this, what can happen is that as you're doing that and you're kind of taking your shortcuts, you might forget. And so you might forget to, put this element stiffness matrix here in the top right, or this element stiffness matrix here, okay? Or you might eliminate the wrong row, or you might go a little bit too fast and kind of overlap 2 entries that are not supposed to be overlapping. And so, there's a lot of kind of small details that can really kind of throw you off in problems like this, where, what I recommend is that, when you're first starting out, go through the whole process. I know it's time consuming. I know it's a lot of writing, but, you kind of need to do a few of these first to kind of really get used to it, to kind of get used to the positioning of, where all the element stiffness matrices are before you kind of do shortcuts like this. Okay. But once you start to get good, by all means, I do this too when I'm doing these problems. I know that these nodes are going to be fixed. And so, I'm not even going to bother. I'm just going to focus on just the top 2 rows of this system. Okay. Okay. And so those are our fixed supports. And so the last thing we need to do is our load. And so if we go back to our problem figure here, our load here has a value of 10,000 pounds. And so that 10,000 pounds is being applied in the negative y direction. On node 1. And so what this means basically is that F1y is going to be minus 1,000 or minus 10,000, excuse me. Okay. And since we don't have any load that's being applied in the x direction on node 1, we're going to have F1x is going to be equal to 0. Okay. Okay, so let's go ahead and add those in, and then we can finally go ahead and solve this monstrosity, no problem. Okay, so F1x can be 0, F1y minus 10,000. Okay. And so with that, our system now is ready to solve. And so we have our 8x8 system, 8 equations, 8 unknowns. We've applied our loads, and so now we can plug this into MATLAB and solve it. Okay. All right. Any questions on this? Yep.
So because it's not a support, change the row.
No, right. Exactly. So you only change the rows when that node is a support. And so because node 1 here is kind of there's no pin support on node 1, it's kind of just free hanging there with just the load there, then we leave that rows alone. All right, and so the next step, I want to say is easy because we've done all the hard part, but even entering this into MATLAB can be a little bit tedious. And so if we use MATLAB to solve this, get the following results. And so we get D1x and D1y. These are kind of the only 2 things that matter. And so D1x is going to be 0.0033 inches. D1y here is a minus 0.0167 inches. Okay. And all of the other displacements because their fixed supports are all going to be 0. So I'll say this is equal to D3x, which is equal to D3 or D4x. This is equal to D3y, equal to D. Right, and so that's the solution. So you know, it's a long process, and when you're doing this on your own, it'll go a bit faster just because you don't have to narrate over it. But you know, it can be really tedious, and so you know, make sure you go slow. Make sure you kind of know you're doing each step kind of carefully, and then that'll help. Yeah, MATLAB saves the day. You know, unless you're well, this one's not that bad because there's technically only 2 unknowns, and so you know, because 6 of the unknowns we know are going to be 0 kind of right away. And so it's actually just kind of a 2 equation system. And so this one's not as bad, but then there are definitely situations where you have, you know, 6 unknowns, 7 unknowns, 8 unknowns. And so, you know, those ones, you really, really need MATLAB to help you out with those ones. Okay. All right. So before we move on to another example, I do kind of want to stop and kind of show you something cool you can do with this result. Okay. And so, you know, we worked really hard to get this result here. And so, you know, it took us a while. We had to set up all the equations and the element stiffness matrices. But you know, for all that work, it kind of seems a bit disappointing that all we get here are just deformations, right? But, you know, we know from ANSYS that there's a lot more that we can get from FEA in terms of things like stress distributions, strain distributions, and all that stuff. Okay. And so let's take a kind of a brief kind of aside here to see how can we compute stress from these kind of nodal displacements. Okay. Okay. Yeah. Oh, yeah. Actually, let me go back a bit. Okay. Okay, so computing stress. And so, you know, I would say, you know, this is probably one of the highlights of using FEA compared to a lot of traditional methods, that you can compute the stress, and ANSYS does it pretty easily. Okay? We're not going to be able to produce kind of a very nice kind of stress distribution that you can see in ANSYS because, you know, we're doing much simpler problems here, but we can still compute the stress in each element. Okay? Okay. All right, and so the formula that we have for that is we're going to say that the stress in the element is equal to the Young's modulus of that element divided by the length of that element, okay, multiplied by, we're going to multiply by a row vector, and so that's going to be minus cosine, minus sine, cosine, then sine, okay? And so remember, these are the sine and cosine of the element's angle, okay? So remember, every element has its own orientation angle, and so you want to make, and so we're basically going to be plugging that angle in here, very similar to how we did it for the element stiffness matrix. Okay? And then we're going to multiply this row vector by a column vector, where this column vector here is the nodal displacement solutions for the nodes that are connected to that element. So it's kind of a mouthful, but every element is connected to two nodes. And so we're just going to plug in the solution for those nodes here. Okay. All right, and so I tried to avoid using D1X, D1Y because I want to highlight that every element is attached to different node. So I don't want you to confuse and say, I need to plug in D1X, D2X, for every single one. Okay. So that's why I did kind of DAX, DAY, DBX, DBY. So that's node A and node B, and where node A and node B are the nodes that are attached to that element. Okay, so let's compute the stress in element A. Okay. And so we can only, of course, we can only really do this for the truss elements. We can't really do this for the spring. Okay. And so we have E over L multiplied by the theta for element A here is 90 degrees, remember? Okay. And so cosine of 90 is 0, minus sine is -1, 0, and then 1. Okay. Then element A, remember element A is connected to nodes 1 and 2, okay? And so the displacements here we're going to plug in are D1X, D1Y, D2X, D2Y, okay? And so if we plug in for this, from up above, we know D1X here is 0.0033 inches. D1Y is minus 0.0167 inches. Okay. And D2X, D2Y are both 0. All right, and so we have a row vector multiplied by a column vector. And so what we have for that is we're going to end up with a scalar because it's basically a dot product between those two vectors. Okay. And so if we perform that and then we multiply by E over L, what we get is 4,175 PSI. Okay. Right. And so since this stress here is positive, a positive stress means that that element is in tension. Okay. All right, so let's do the same thing for element C. Remember, we can't do element B because element B is a spring. Okay. And so elements, I said we can't do element B, but it's still theta B. Okay. So theta C, remember, is 90 degrees. Okay. And it's connected to nodes 1 and 4. So theta C, or sigma C here is E over L multiplied by, we have cosine, minus cosine of 90, which is -1. Yeah. It is 0, thank you. Getting hungry. Okay, and so cosine, minus cosine of 0 is -1, minus sine of 0, which is 0. Cosine of 0 is 1, and sine of 0 is 0. Okay. And then we're going to multiply this by the nodal displacements for element C. And so element C here is attached to nodes 1 and 4. And so we have D1X, D1Y, D4X, D4Y. Okay. So go ahead and plug in. Okay, and so if you plug in all the displacement numbers, what you're going to get is a minus 825 psi. And since the stress here is negative, the element is in compression. Okay. And so that's kind of a quick and easy way that you can compute stresses in these direct stiffness systems. It's fairly crude, and so we're kind of just limited by the size of our elements here. But this is kind of what we expect from finite elements, is to be able to compute stresses like that. Question: why did we skip B? And so we skipped B because it was a spring, and so we can't compute stresses in a spring just because the spring is kind of coily and it doesn't have a constant cross-sectional area and everything like that. Yeah. Mhm. All right. Any questions on this? Okay. All right. And so we have about 20 minutes left in class. And so unfortunately, I think we're going to have to start an example and leave it for next time again. But I do want to cover this example before we move on to beams. Okay. And so for this example, I'm going to introduce a new kind of support. And so, now that we're in 2D, we know that in 2D, every node has 2 degrees of freedom. So it has both an X and a Y displacement. So far, in the last example that we did, we saw that when you have a completely fixed support or a completely, a pin support, that's going to zero out both the X and the Y displacement. Okay? But there are some types of supports that can only knock out one type of displacement, and that's a roller support. Okay? Okay. And so a roller support, may look something like this. And so it's like a roller skate or a traffic cone on wheels, whatever you want to call it. Okay. And so unlike the fixed support or unlike the pin support, the roller support is only going to cancel out one direction of the deformation. And the component of the deformation that it's going to knock out is whichever direction is perpendicular to the surface. Okay. And so I get asked this every year. And so, if it's a roller support, it makes sense. It makes sense that the roller support is going to prevent any deformation going into the ground like that. But in theory, if this was just, a traffic cone on wheels, you could actually lift it off the plane, right? You're technically right, but then, the convention is that the roller support constricts it completely in that direction. So what I imagine is that, imagine this is on a track. And so the wheels are kind of in a track like that. And so kind of the upper and lower track prevent any deformation up or down, but it can still slide left to right in that direction. Okay. To prevent, in this case, it's going to prevent Y deformations going up and y deformations going down as well. Okay. And so of course that's going to change how we do our boundary condition setup, because now instead of knocking out 2 rows, okay, and then fixing those, we're only going to knock out 1 row in the global linear system. Okay. Okay, so let's go ahead and do an example here and see how this is done. Okay. All right, so this one's not gonna be as crazy as the last one. So this is only gonna be a 2-element, 3-node system. Okay. So we're gonna have a vertical wall. And so on the one hand, we're gonna have a fixed support up here. Okay. So this is gonna be element A. We're gonna have a node here at the end. It's gonna come over like that. It's gonna be element B, okay? And then attaching element B to the wall is actually gonna be a roller support. And so that Y direction is gonna be free for node B right there, okay? Okay, so let's go ahead and finish labeling this. And so we have the nodes labeled. We also need we have the elements labeled. But we also need to label the nodes as well. So I'm gonna call node 1. Node 1 is gonna be the node on the far right. And so that's gonna be where the 2 elements converge. Node 2 is gonna be the top node, which is fixed. And node 3 is gonna be where the roller is, okay? Okay. Let's add some dimensions here. And so we'll say element B here has a length of 5 feet. Element A here is gonna have a length of 10 feet. Okay. And the angle between these elements is going to be 30 degrees. Okay. Okay. And so we'll say both elements have the same material properties. And so they're going to have the same Young's modulus. And so the Young's modulus is going to be 30 times 10 to the 6th psi. And the cross-sectional area, A, is just 1 inch square. Okay. And then in terms of loads, we have a single load. So we're having a load on node 1 here. And so that's going to be 25,000 pounds. Okay. And that's going in the vertical direction. Okay. All right. And so just like the last example, what we're interested in here is values for the nodal displacements. Okay. And so that's going to require us to go through the direct stiffness method. And so we're going to go element stiffness matrix, assembly, boundary conditions, and solve. Okay. I'm going to go a little bit faster on this one just because it's a simpler system and we've kind of seen this already. There are a couple nuances to this that we haven't seen before though. So I'll make sure to pause on those ones, but for the rest of it, I'm going to go a little bit fast. Okay, so before we begin solving this problem, are there any questions on just the setup for the problem? Okay, all right, so let's go ahead and start writing out the element stiffness matrices. Okay, and so let's start with element A. Okay, and so before we write out the element stiffness matrices, we have to. I mean, the first thing we have to determine here is what the orientation for element A is, right? And so we need theta A. All right, so here's where it gets a little bit tricky. So you kind of have to you kind of have to look at the geometry a bit carefully, and you have to look at the labeling really carefully as well, because that's going to determine this as well. Okay, because if you look at this figure right here, right, you see element A, it's consisting of nodes 1 and 2, and it's angled kind of upwards and to the left. Okay, and so the tempting thing to do here is to say that theta A is 30 degrees, because that's the angle that we see exactly in the figure, right? But of course, I'm doing all this buildup because it's actually not 30 degrees. Okay, so let me go ahead and draw another figure here to kind of show you why it's not 30 degrees. Okay, and so we'll go ahead and draw element A here, kind of separated from everything. Okay, and what I'm going to do is I'm going to draw an arrow that goes from the lower numbered node to the higher numbered node. Okay. Right, and so you're going to want to draw an arrow from the lower node to the higher node. Okay, and that's going to be kind of like a vector that's going to define the direction for that element. Okay. Next, what I'm going to do is I'm going to overlay the positive x-axis on this element, starting at the lower numbered node. Okay. So what I did here was I overlaid positive right? And so in this case, the lower numbered node is node 1. And so I'm going to draw a horizontal line that goes to the right, okay, because that's the positive x-axis. Okay. If you remember from earlier today, what I said was that the angle that we actually use in the element stiffness matrix is the angle that's formed between the element and the positive x-axis. Okay. And so if we look at the angle here, okay, if the positive x-axis starts at node 1 and goes to the right, then the angle that we actually want is actually this obtuse angle here. Okay. So that's what theta A is. Okay. And so you can see from this figure that it's not 30 degrees. Okay. Question: can you also go the other direction and just have it as a negative value? Yeah, you could. And so you can use negative angles here as well. And so this, of course, is going to be a counterclockwise rotation. And so going from the positive x-axis to somewhere else, that's counterclockwise. But if you want to use a clockwise rotation, then you just make it negative. Yeah. Yeah. And so with this convention here, we can see that the theta A here is actually going to be, if we kind of draw kind of an imaginary line here, because we know this angle here is 30 degrees. Okay. And so theta A here is going to be 180 minus 30 degrees. And so the angle that we actually use here is actually going to be 150 degrees. Okay. So this part is really tricky. And so you have to be careful in terms of how you choose your angles. And so, do the little trick here with drawing the arrow from the lower node to the higher node, draw your positive x-axis, and then just rotate counterclockwise from there to the point where you're at. Okay? And so the theta here we're actually going to use is 150. Any questions on that in terms of how we did that? Okay, and so now that we know that theta A is 150, we can go ahead and follow the same process as before. And so cosine of 150 is a minus √3/2, and sine of 150 is a positive 1/2. Okay. And so if we plug this into our element stiffness matrix, so we say Ka, Ka is AE over L, which is 2.5 times 10 to the 5th. 3/4, 3/4, 0.4, 3/4. Okay. So I know I went pretty quickly with that, but a lot of this just kind of plugging and chugging. So it's the same element stiffness matrix formula with all the cosine squared, sine squared, cosine sine. This one's a little bit annoying because you have a √3/2 and a 1/2, and you have to account for a minus. But like I said, do these slowly, and it'll be okay. Okay. And so, of course, element A here is connected to nodes 1 and 2. And so we have D1x, D1y, D2x, D2y. Okay. And so that's going to be the element stiffness matrix for element A. Okay. Very quickly, let's do the element stiffness matrix for element B. This one's going to be a lot faster because it's a horizontal element. Okay. All right, and so if we draw element B here, element B is connected to nodes 1 and 3. And so if we do the same trick as before, where we draw kind of an arrow that points from the lower node to the higher node, and so we draw a node from nodes 1 to 3, we can see here that if we draw the positive x-axis this way, in order to get into this orientation, we have to rotate by 180 degrees. Okay. And so theta B here is going to be 180 degrees. And so cosine of 180 is, of course, going to be -1. Sine of 180 is going to be 0. Okay. And so if we plug that in, we get KB is equal to 5 times 10 to the 5th times 1, 0, -1, 0, 0, 0, 0, 0, -1, 0, 1, 0, 0, 0, 0, 0. Right. So I know I did that at light speed, but this one's fairly simple because it's a horizontal line. So a lot of it's going to cancel out, and you're going to get just 4 entries in the global or the element stiffness matrix for that element. Okay. We scroll up so you can see both in case you're still writing down. All right. Any final questions on this before we wrap it up for today? Okay, all right, so I'll go ahead and leave this up for the next few minutes until Professor Gary kicks me out, just because I know it's a lot to write down. But we'll start with this next time as well. So don't feel pressure to write all this down. I'll go ahead and start up with this just so you can finish there. Okay. right, so thank you everyone for coming today. Thank you everyone for for tuning in. Hope you guys enjoy the rest of your evening, and I will see you on Thursday. No, the midterm is not going to be until midterm exam, or you're talking about the midterm project or the midterm exam?
Yes.
The midterm exam is going to be the Thursday before Thanksgiving. And so we still have a few more weeks for that. So I think three more weeks. Okay, I need to update the syllabus then. So yeah, I don't plan on giving the midterm exam until Thursday before Thanksgiving. Yeah, thanks for catching that. Yeah. This one has so L is down. This one has. Yep. I think, yeah. Okay, yeah, thanks, Charles. Yeah, I think that was my original plan. I think I forgot to update the syllabus from last year. And so this is last year was the first time I kind of did both the midterm project and the exam. And so I made that plan at first, and then we got to this point. I'm like, no, there's no way it's going to happen. There's no way we could take a midterm exam right after the project is due. So that's why I pushed it. Yeah, I was a little bit, I guess I was a little bit lazy updating my syllabus this semester. Yeah, but it'll be before. Oh, I see. Yeah, good thing we're pushing it back.
So I sort of plan around.
Yep.
Okay. And yeah, see more.
I think it's because for the bearing mode, it can only be one. It can only be one thing. So you want to pick kind of the largest space that makes a complete circle. So
it seemed like it didn't have another. It would be like the main surface for the bearing. Actually, even when I go slow, I don't know if it's because it's a curved surface.
I think it was because it's not. That's weird that the other one works, but I think maybe it's because it's not, because the one that you selected before, kind of covered by this part here, but it's actually a complete circle that's kind of covered. But this one is not, it's kind of cut off. So I think that's
So
probably
it's like a
why.
discontinuous surface.
And so the other one will work just fine, because if it's this one. The only thing that we might have to do is stress on this one. That's okay. The most cases, we're going to certainly stress it out. So it's not ideal, but
That still applies. Okay. I was wondering, let's see it highlighted, so okay.
yeah, it should be under here.
Yeah.
So I think that's kind of this, but the very surface you need a full circle.
So is this a spiritual pairing style, or is this?
It's a great question that I don't know.
Okay. I was like, how do you even get a bearing in there? It's tapered the surface.
Yeah.
It's a good question. Okay. Well, I'll just have to go with that then. It's like my what? It's like 2 million mesh, so.
Oh, yeah, 2 million, yeah, that's way too much.
Just seeing what I'm doing. Okay.
Other questions?
Not the relation of the project, it mentions like to have a clear. Basically, I just wanted to say, Well, I wanted to see, like, I want to see the reason why most brackets are made of stainless steel. And I wanted to see if maybe I can find, if I, first I want to understand the timeline, I have an idea as to why, because steel is known to be a very strong material. But I also want to see if maybe we can get away with something like aluminum, or I don't know, any other alloy of steel that's, I don't know, like, the reason is maybe that it can help save manufacturing costs. So I guess my question is that a recent, or I mean, is that a decent objective?
That's perfect. That's exactly what.
Okay.
So basically, you're doing FA with a purpose. You have this geometry, you have some kind of loads that can be, that's sort of.
Yeah.
And you want to find out, if I change the material, is it still going to hold up without actually making it. That's the whole point of FA. It's a simulation. That's exactly what.
Okay, cool. Thank you. It's good to hear. Thanks.
Okay, yeah, I'll update them, Charles. Yeah, usually they can update that because I think they know that exam times can change, and so yeah, I'll make sure to follow up on that. All right, Charles, sir, up any final questions? Okay, all right. I'll see you guys next Thursday then.